Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing our examination of the reactions of carboxylic acids. In the last scribblecast lecture, we looked at the predominant feature of carboxylic acids, that is their acidity. But carboxylic acids have reactive properties that extend beyond the simple acid-base chemistry that is observed for carboxylic acids. One important reaction is esterification, and we want to look at that now. Esterification reactions involve the reaction of a carboxylic acid, such as ethanoic acid or acetic acid, with an alcohol. Now this reaction takes place in acid. We react it in acid and we can establish an equilibrium. Acid and heat, and we can produce ester. In this case, if we take ethanol and react it with acetic acid, we can produce ethyl acetate, or what is sometimes called ethyl ethanoate. Water is given off in this reaction, and because it's an equilibrium, it's advantageous to remove the water to drive the equilibrium to the right. Water will, as we learned in the preparation of carboxylic acids, cause ester, which is a carboxylic acid derivative, to convert back to carboxylic acid. Now, if we take this molecule, acetic acid, can we do the same reaction in base? And the answer is no. Because carboxylic acid, even in the presence of ethanol, is an acid, base will not deprotonate the alcohol, producing a larger or stronger nucleophile, but rather the base will deprotonate the carboxylic acid. Once that happens, you end up with the acetate anion. And even though oxygen is electronegative, the negative charge on the oxygen lowers the electrophilicity of the carbon, making it less susceptible to nucleophilic attack. Because of the negative charge, there's less likelihood that a weak nucleophile, like the alcohol, will undergo nucleophilic attack. So you will not get ester formation in base. Very important to realize that. So how does this reaction occur? How does the esterification reaction between alcohol and carboxylic acid actually proceed? Well, we can envisage several possible reaction mechanisms. For example, we've all had experience with alcohol chemistry. We learned that alcohols must be reacted in acid to turn the OH into a good leaving group. For example, if we protonate an alcohol with H+, which is reversible in an equilibrium, a molecule like ethanol can form a good leaving group. We can imagine ethanoic acid then attacking the ethanol. Actually, we should write that in. The protonated ethanol. Because we have such a good leaving group, And because it's primary, we could go SN2 and kick out water. Plus water. And then lastly, of course, we could deprotonate actually, let's raise this a little bit. Minus H plus. So top reaction was plus H plus. And we have CH3, C double bond to O, and our ester. And so we have some steps here. Two steps, which are step 1, protonation. Step 2, of course, being SN2. And step 3, deprotonation. Note step 1 and step 2 are not part of the SN2. There are steps that only occur when they're necessary. Okay, so we've got step 1, step 2. There we go, 3 steps. Certainly, this represents a possible potential mechanism for explaining or rationalizing the formation of the ester. However, I certainly could, rather than looking at alcohol chemistry, take a note from what we learned in aldehyde chemistry. What's that? Well, I can look at it from the view of the carboxylic acid. What can happen if I throw acid in presence of a carboxylic acid? Well, we learned in aldehyde chemistry that if you add acid, it's possible to reversibly protonate the lone pairs on the carbonyl. In so doing, get a positive charge here, right? And I can draw some resonance structures here. I can move the pi electrons out to the oxygen, make a lone pair. If I do, I get this. And if I continue, I can draw another contributor. So I can get resonance stabilization. Now I can make the carbocation undergo nucleophilic attack now. Okay, so I can bring in methanol. Actually, let's move it over here. And did I say methanol? I mean ethanol. Let the ethanol come in with its lone pairs and attack the positive charge. If it does, you get this. And of course, I think I'm going to run out of room. In fact, I'm almost positive I'm going to run out of room. So I might take some shortcuts. You still have the H here, plus on oxygen. Now you can see if we remove it, that's reversible, losing ethanol. We can deprotonate. That would take a H plus off. And of course we could go back and put the H plus back on the ethanol. But if we do two steps at once, because I'm running out of room, we can add H plus on the OH. So we take a H plus off the ethanol and put an H plus on the OH. And we get a good leaving group. Now we have OCH2CH3. Again, if it leaves, we get a carbocation, and that carbocation, I can draw the same resonance structures as I have up on top. But I'm going to just bring that lone pair down and kick it out. I'm going to draw one. I'm not going to draw all three again. Kick out the water, so minus water. And what do you get then? You get this guy. Okay. So water's removed, and now we have this protonated ester, so we're almost done. We just remove H plus now. And by the way, I'm going to draw a red circle so you can know this guy is resonance stabilized, just like these structures. Okay, so I could draw the same structures. The only difference is instead of an OH here, it has the OCH2CH3. And there's lone pairs, and I can create the three resonance contributors for that structure, but I'm not drawing them because I've run out of space, and I want to keep both mechanisms up for comparison purposes. And so I can now draw the final product, of course. When we lose the proton, we do get the final ester. Now what's interesting about this is we've got two different mechanisms. One that I might call based on substitution nucleophilic bimolecular with some protonation deprotonations is SN2. This one, I might call it a nucleophile, so nucleophilic. And the nucleophile is the ethanol, and it's attacking a C double bond O. It's attacking an acyl group. And then we're kicking out, after it attacks, we kick out water. So substitution. Nucleophilic acyl substitution. So the bottom mechanism could be referred to as nucleophilic acyl substitution. The top one's SN2. And these reactions, mechanisms, are both very different proposals. Now, as you know, we can never prove a mechanism right. Mechanisms are postulates. They're proposals as to how a reaction might proceed. But A mechanism must explain all observable phenomena recorded in investigating a reaction, and if there's something contrary to experimental evidence, then you can rule out a mechanism. And although at first these mechanisms appear to be similar, you should note there is a subtle difference. What is that difference? Well, what I want you to do is I want you to follow what happens to the oxygen on the alcohol. You see, we can purchase ethanol in which oxygen 16 has been replaced with oxygen 18, an isotope of oxygen. Oxygen 18 has a nuclear spin, and hence it can be investigated or studied through nuclear magnetic resonance spectroscopy. And so if I label this and say, okay, well, we're going to look at the NMR signal of oxygen 18 in ethanol. If you follow it in the SN2 reaction, just label the oxygen on the ethanol and see where it ends up. You see it ends up in the water. If, however, you follow the oxygen on the ethanol in the nucleophilic acyl substitution mechanism, you discover a different location for the oxygen of the ethanol. In the nucleophilic acyl substitution, the oxygen of the ethanol ends up in the ester. In the SN2 reaction mechanism, it ends up in water. If you investigate this reaction and you do an NMR spectrum, the oxygen 18 signal shows 100% presence in the ester. What this means is nucleophilic acyl substitution is the supported mechanism, and the SN2 proposal is wrong. Okay, so esterification is an important reaction, and it is thought to undergo or proceed through a nucleophilic acyl substitution reaction mechanism. We only could do it in acid because if you try to use base will deprotonate the carboxylic acid, and the negative charge present in the carboxylate prevents or slows down nucleophilic attack. And there is no viable loss of water possible. So, having done that, let's continue with our reactions of carboxylic acids by examining reduction reactions. Now, we've talked about reductions in aldehydes and ketones, and one of the reducing agents we looked at were metal hydrides. And there were two hydrides, sodium borhydride and lithium aluminum hydride. It turned out that the carboxylic acid is so oxidized it needs a more powerful reducing agent, and while sodium borhydride is good for aldehydes and ketones, it's too mild to be effective with carboxylic acid, so it's typically not used. We use the more reactive reagent lithium aluminum hydride. Now, lithium aluminum hydride, when reacted with a carboxylic acid, will add H- to the C double bond O. And when it does add the H-, to here, you're going to eventually kick out the OH and add a second H- and get to an alkyl oxide. So if we use lithium aluminum hydride here, the reduction, and this is usually done in ether, will get you to an aluminum salt of CH3, CH2, CH2OH, where the OH is the oxygen of the C double bond O, and that's usually an ether. Then you add acid, oops, where the O is from the C double bond O, and that's an O minus, not an OH. When you add acid in the second step, you protonate the alkoxide, making your alcohol. So reduction of carboxylic acids will produce primary alcohols. So overall, we write this reaction as a two-step process, integrating multi-steps by numbers. First, lithium aluminum hydride and ether. Followed by H3O plus. We've examined a mechanism of lithium aluminum hydride reaction in aldehydes and ketones, and with cyanohydrin chemistry in aldehydes and ketones. So we're not going to revisit the reaction mechanism here. What we want to do now is move on and examine chemistry of dicarboxylic acids. Reactions of carboxylic acids will be revisited when we look at the carboxylic acid derivatives. And we want to, before we continue with carboxylic acid reactivity, examine some of the chemistry of dicarboxylic acid systems. Of course, before we look at the reactions, we really need to examine some of their nomenclature. Now, it's not a true dicarboxylic acid, but it fits in somewhat because it's diprotic. And so we're going to include carbonic acid, so we're going to put common, IUPAC, and then we're going to put pKa1 and pKa2. If we take carbonic acid, its pKa1 is 6.4. pKa2 is 10.3. The loss of the first proton is somewhat reduced by the resonance, which we've looked at previously. Resonance donation of the lone pair off 1OH. When it dumps in, it creates a dying negative, and this destabilizes the anion, making it less likely to lose a proton. The first true dicarboxylic acid we want to look at is called Oxalic Acid. Oxalic acid is ethane dioic. Ethane dioic acid. Now, the pKa1 for oxalic acid is 1.2. It's a very low value, which indicates it's quite a strong acid. Much stronger than typical pKa 4 to 5 value of carboxylic acids. The second pKa of 4.2 is more typical of what you expect for carboxylic acid. In order to understand this pKa effect, we can localize one carboxylic acid and say, look, this is like an NO2 group. This guy has two oxygens off of it, which are electronegative, putting a delta plus on this carbon. The CO2H is very electron withdrawing. Because it's electron withdrawing, it will help stabilize the resultant anion that forms. Since the anion is stabilized, the loss of a proton is favored. Hence, the pK is lowered and it's more acidic. If we put a CH2 between our C double bond O's, we end up with what is referred to as malonic acid. Or propane dioic. Now, if we look at propane dioic acid's pKa values, we notice its first pK is not quite as acidic as we saw in oxalic. This is consistent with what we've seen happen as you move electronegative groups further away from the carboxylic acid. If we take one of the CO2H's and treat it as an electronegative group, because we're moving it away from the other CO2H, the electronegativity doesn't stabilize the anion, resultant anion, as much as it normally does. And in the case of malonic, it's further away than oxalic, so pK is not quite as high. This is further observed in the next acid, in which we have two CH2 groups. I'm going to just put CH2 twice in brackets. If there are two CH2s between the carboxylic acids, you have succinic acid. Now, succinic acid, or as IUPAC would call it, butane dioic acid, moves the electronegative groups further apart, and as a result, you start achieving normal pK values, 4.2 for the first one and 5.6 for the second one. You notice that the loss of a second proton, the pK is much reduced. This is because the molecule already has a negative charge. Putting a second negative charge makes it harder to pull the proton off. If you like, you think of the first negative charge as helping retain the proton. You should also note that the presence of two negative charges on the molecule is somewhat destabilized by electron-electron repulsion between the two negative charges. Next one, pentane dioic acid, or when we have three CH2 groups, has the common name glutaric. Glutaric acid. Glutaric, or as the IUPAC would say, pentane dioic acid. pKa for pentane dioic is 4.3 and about 5.4 for the second pKa. And the next two, that should have been a 3. We have For hexane, we have what is called adipic acid. Adipic acid or hexane dioic. pKa 4.4. And the last, of course, dicarboxylic based on alkanes is going to be heptane dioic. Of course, that's going to have 5 CH2s. And that's called Pimelic Acid. Pimelic acid is heptane dioic. pKa of heptane dioic is 4.5 for the first pKa and 5.4 for the second one. Okay, now we're going to look at some more of these dicarboxylic acids, but you've got quite a few common names here to remember. And so I want to give you a memory aid, often to help remember the number of carbons, starting with 1 carbon. If you remember the term COMSGAP, C-O-M-S-G-A-P, and then you just count 1, 2, 3, 4, 5, 6, 7. You can always remember a dicarboxylic acid with that many atoms, so count the letters COM. So you know malonic has 3 carbons in it. It must be a propane dioic. So this memory aid, COMSGAP, can be useful in helping you retain the common names, which are very important to know. And you are required to know both the common and IUPAC names. Now I want to keep one of the carboxylic acids, which is succinic, and so I'm going to rub these off and do a comparison now with a couple other carboxylic acids. Obviously, one carboxylic acid that we want to look at is the dicarboxylic acid based on benzene. And remember, we learned that this dicarboxylic acid has 2 common names, which we've already covered. You can call it orthophthalic acid, or you could call it just phthalic acid. both are possible. The IUPAC name was based on the name of the alkane ring, and so it's called benzene hyphen 1,2 hyphen dicarboxylic. So benzene 1,2 dicarboxylic is all one word. Acid. And what is the pKa of this dicarboxylic acid? The first pKa, of course, is 2.9. And the second pKa is 5.5. Certainly, I could draw it this way. Some of the increase in pKa value is due to the electronegativity, but also, if it deprotonates, there will be some effective hydrogen bonding, intramolecular hydrogen bonding in here. And that probably contributes to the low value of the first pKa as well. Now, let's look at two related to succinic, if we can. And these are dicarboxylic acids that you actually saw in first semester in the molecular models course. For example, we could have CH double bond CH, C double bond OH, C double bond OH. When the two carboxylic acids are in the cis configuration, this is referred to as maleic acid. If you like, it is cis but 2 enoic, that's all one word, acid. And it has a pKa of 1.8 and 6.1. If you draw the trans version, remember that was called Fumaric Acid. And that is trans but 2 enoic acid. Its first pKa value is 3.0. Okay. And then its second is normal, around 4.4. Okay, so we've got an anomaly if we compare pKa's. Well, first off, let's compare succinic acid, which doesn't have the double bond, to the fumaric acid, which has the trans double bonds. This suggests that the delocalization of side-to-side overlap of the conjugated double bond system, this pi system, helps facilitate, if you like, the effect of the electronegativity. That is, electron withdrawing effects are further supported by the conjugated double bond system. So when this negative charge forms, you lose a proton. The negative charges on the oxygens are further stabilized by the electronegativity of the carboxylic acid through the conjugated double bond system. It's a small increase, but it's significant, lowering the pKa by about 1.2. So it suggests that the pi system helps increase the acidity a little bit. But something really strange happens when we go to maleic acid. Just going from trans to cis causes a huge jump. If you like, in the acidity of pKa1. But then pKa2 is significantly lowered. The number's higher, but the acidity is lowered. In other words, the first one, the acidity is increased, but then the loss of the second is lowered. The question is, why? Why would that happen? Well, let's take a look and see if we can understand this by first considering succinic acid. Let's try drawing succinic acid. When succinic acid deprotonates, one end will form a carboxylate anion. Indeed, when that happens, we're going to get something that looks like this. We're going to have an O minus. We're going to have an O double bond down here. Here's a CH2. Here's a CH2. Here's a COH, if you like. And there's a double bond O here. And what's possible in all of these structures is for the molecule to bend in a hydrogen bonding interaction set up between the H and the O negative. This will somewhat help stabilize it, but in this case it's not very effective. First off, the ring structure is not optimal. There's a lot of atoms. Remember, 6-membered rings in sp³ systems seem to be optimal for chair conformers. 1, 2, 3, 4, 5, 6, 7. We have 7 atoms. The second thing is sigma bonds are free to rotate. If you rotate the system, this will drag the OH down here, out of the way. It's too far away for hydrogen bonding interactions. And so simple conformational change will reduce the time, if you like, spent in this attractive interaction. And the net result of that is there's not a lot of stabilization in the pKa. Now let's change this scenario. Let's remove 2 hydrogens and put in a pi bond. Pi bonds result in hindered rotation. This hindered rotation locks the OH group into this position where it could interact with the CO2 minus, leading to hydrogen bonding, which stabilizes it. Removing the conformational change, locking the hydrogen for a hydrogen bonding interaction into close proximity, stabilizes the anion. A stabilization you can't get when you have the trans and the CO2H is pointed on the other side. And so you get a significant increase in acidity. But that same hydrogen bonding, which lowers the first pKa, that same interaction with the negative charge is going to make it less likely to lose the H+. Thus, you see an increase in the pKa value, a decrease in acidity. For the second pKa, the loss of the second hydrogen becomes less likely. So, the increase in acidity for pKa1 and decrease in acidity for pKa2 of maleic acid can be attributed to the hindered rotation of this double bond. And that hindered rotation locking the hydrogen into a position where it can interact through hydrogen bonding with the CO2 minus. Okay. Well, we do have several interesting reactions of dicarboxylic acids that we want to examine. But we're going to examine the chemistry of dicarboxylic acids in the next Scribblecast lecture. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.